Okay, so good afternoon. First, as usual, I check that the recording is okay. So can you hear me from home, anybody? If you hear, write on the chat. Yes. Okay, so we can start. Just a summary of what we did last week. Well, depending on the course, we discussed multinomial classification models, and in particular, we discussed how to use multinomial and categorical, which we actually showed are very, very, very related to solve problems with discrete features. Those who are from the 01 HERU course do not have this part on categorical density, so what we saw last week for them, it's just the Gaussian models. Other questions on these parts. So we have seen that both the categorical and the Gaussian model belong to the class of generative models, and are ways to perform classification by building class conditional densities that then we can use to perform inference by applying Bayes' theorem. So combining the class conditional with prior information gives us class posterior probabilities. And then we can use class posterior probabilities, we said, to select the class which has highest posterior probability. Other questions on this part? Okay. Then today we will take a break from classification models. We will come back to classification models actually after holidays, because with the schedule that we have now, we will have this week this lecture. Tomorrow we'll have the laboratory on the categorical models, and next week we will have, well, of course, the categorical model laboratory is only for computer science students, and then we will have the week after, the next week we have only Thursday, and we will have the laboratory on today's lecture. So we will come back after Easter with the next model. What we will do now in this part, last theory part before the break, we will discuss how we evaluate models, and how this is closely related, how we make decisions when we use a classification model. We have discussed, as I said before, up to now we said our goal is to compute class posterior probabilities, for example, for a 3-class problem like the iris dataset, or if you prefer, counting from 0. For the iris dataset, we would compute the posterior probability of the 3 classes, and then we would assign the sample to the class that has highest posterior probability. And then we said we would measure how good is our decision, well, are our decisions plural, because we have multiple samples, by computing the accuracy over an evaluation set. Now, today we will go more into details on how to do proper evaluation of the models. We will see that accuracy, for example, has lots of limitations in what it can represent. So we will need to extend beyond accuracy to find better ways to measure our performance. And then we will see that that thing is closely related to how we make our decisions. So up to now we said we assign the class to we assign to the sample the class that has highest posterior probability, and we said every time when it was this at the beginning when we were saying this, I always said for the moment, because we will see that this is optimal under some assumptions, but we will show that using the class posterior probability is not by itself optimal for all possible use cases. And we will discuss how to improve on our decisions, and we will see that the two things are closely related. We will try to perform optimal decisions and measure the goodness of these decisions in the context for which they are optimal. Okay, here you have a first example of why we can't, and as I said, these two will be interleaved, so we will start discussing decisions, then we will switch to model evaluation, and then we will go back to decisions. So the two parts are interleaved because they are strongly related. But before we get to the model evaluation part, let's see, well, for both things, let's see why what we did up to now is not necessarily a good thing. Let's start with questioning the way we made our decisions. We said, if we have a multi-class problem, then let's compute class posterior for all the classes, and then let's imagine that these are the outputs. Then we would assign the point to class 2 in this case, because that's the class that has higher probability of being the class of the sample. However, if we make a mistake, it means that we label as class 2 a point that is from class 1 or class 3. Now, saying like this with numbers doesn't really give us an idea why this is not correct, but let's cast this as a real problem. Let's imagine this is a diagnostic system that is used for health and care, so to decide whether somebody should be treated because he is ill or not. So it's a system that should help a doctor, or ideally, but since given how they work, hopefully not too soon replace the doctor themselves. Let's see what is the problem. Now, if we have a diagnostic system, it can give two answers. It can give answer that a patient is healthy, so it needs no treatment, or it can say that the patient is ill, so it's a binary problem. Healthy or ill. These are the two possible predictions. Now, let me draw it somewhere else. Draw it here. We can have healthy and ill. These are the possible predictions. And now these predictions can be given to what? To a healthy patient or to an ill patient. So this is the real label of the patient. So you may have the condition where an healthy patient is labeled as healthy, so everything is correct. An ill patient is labeled as ill, and everything is correct as well. And then we may have two different kinds of errors. An ill patient is labeled as healthy, so I say this is somebody who is ill, but I don't discover that he's ill, so I'm not treating him. Or I can have a patient that doesn't need any treatment, but by mistake I label him as ill. So I say this patient needs treatment, while he actually didn't need the treatment. Now, depending on the treatment and the illness that the patient has, these two errors will have different impact on the person. If it's an illness that is not critical, it's not important, it's something very light, then treating the patient unnecessarily is going to give him some medicament that may have adverse effects on the body, while not treating the illness is maybe something that will not give serious health issues. So in this case, treating an healthy patient may be more expensive than not treating somebody who is ill. If it's a serious disease, then saying to somebody, you are healthy, you don't need treatment, may put that person in danger of life. So treating somebody who is healthy but doesn't need treatment, of course, has a bad impact on that person's health. But not treating somebody who is ill has a much more bad effect on the person. So making a mistake of the kind, I don't treat an ill patient, may be much more expensive because it may lead to the person dying than treating somebody who's not ill. Of course, what we would like is to avoid both kind of errors, but we will see that this is typically not possible. We will still have this kind of errors. We will see that we will be able to trade off this kind of errors. So we will see that, for example, it will be possible to decrease the number of ill patients that I don't treat by increasing the amount of healthy patients that I treat. For example, trivially, if I treat everybody, I don't have any error of the kind illness patient that is not treated. Of course, all the healthy patients now will be treated. That's the idea behind vaccines. I treat everybody because the effect of treating healthy, so somebody who doesn't need the treatment, are very low. The risk of not treating somebody who is ill, so who may develop the illness, is much larger. So it's better to treat the whole population. So these kind of things are not the same. So just looking at the class posterior probability in this case is probably not the best thing to decide whether the patient is ill or not. For example, let's imagine that my system says that the probability of being ill, given the person, so given some features that represent the analysis, etc., is 0.5, and the probability of being healthy is 0.5. But if I don't treat, and Alice was ill, then she will die, then in this case I would probably decide that it's better to treat her in any case, just to be on the safe side. So I will not use the posterior probability alone, even if they are slightly biased towards being healthy. So for example, this is 0.4 and this is 0.6. Still I have, if I don't treat her, I have 40%, according to my prediction, probability that she will actually be ill. I don't treat her and she will die. So probably I will decide to treat, even if the probability that she needs the treatment is lower than the probability that she doesn't need the treatment. And we will see how to find where we need to put our threshold to decide when we should treat or not. Now, connected to this is also the problem of how we measure the goodness of our system, which will show similar issues. So for the moment, keep this example in mind. We move to evaluation, and we see what are the issues of evaluations. Then we will come back. So we will take a long detour and then solve this first problem at the end. Now, the first thing that we do is we look at how we measure the performance. Why? Because essentially to decide what is a good decision, I need to know how I measure whether the decisions are good. If I don't know how I measure, I cannot say what is good in terms of improving my performance. So the first step to obtain optimal decision is to decide how I measure the decisions are good. So we start looking at the second part of the problem. For the moment, we have discussed in laboratory accuracy and error rate. What are these? Well, we said, let's take an evaluation set, make predictions on the evaluation set, count on the evaluation set the number of correct classifications, divide that by the number of samples. This gives us the accuracy that you can say can be interpreted in a frequentist way as, if I pick randomly one sample of my dataset, what is the probability that my prediction for that sample will be accurate? And the error rate, which is 1 minus accuracy, is just the number of wrong classifications divided by the number of samples. So one step towards making optimal decisions could be try to optimize this matrix. I want to minimize the number of errors on my evaluation set. Now, accuracy has actually several problems if we use it like this. For example, we just discussed not all errors are equal. How is accuracy defined? Number of incorrect classified samples divided the number of samples. So if I go back to my healthy, ill patient scenario, every healthy patient labeled as ill will account for one error, but that's the same as any patient that is ill and is labeled as healthy. So those mistakes, if I use this expression, every time I have one mistake, I will add 1 to the numerator, regardless of the kind of mistakes. So both mistakes weight the same. Then the error rate depends on the empirical class prior of the evaluation set. Let me see if I write it here. No. We'll see an example, but just to see what it means. Imagine that I have 1,000 healthy patients in my data set and 10 ill patients. Now, if I make 10 mistakes over the healthy, so 10 healthy people are labeled as ill and 2 ill people are labeled as healthy, what do we have? Then the number of errors is 12. But we can see that if I concentrate on each class on its own, 20% of the ill people are actually wrongly classified. Now, if I have the same proportions, so here will give me an error rate of 12 out of 1,010, so around 1.2%. Now imagine that I have 100 healthy and 100 ill patients. And then still I make mistakes for 20% of the ill patients, and the same as for the healthy as before. Now the number of errors are 210 divided 2,000. So the error rate now is around 10%. So depending on the number of samples that I have of the two classes, my error rate will change. And what is the weight that I'm using here? Well, we will see the error rate implicitly employs the empirical prior of the training set. So if I make 20% mistakes for the ill class, in the first case, the ill class will weight 1 out of 101, because that's the prior for the ill class in my evaluation set. But we've already discussed during training that typically the priors of our evaluation set do not represent our target application. Why? Because in reality, I may have very unbalanced scenarios where most of the people are healthy and few are ill. But typically, my evaluation set will have balanced classes because I want to have errors for the two classes, enough errors over both classes to be able to make a robust estimate of my error. So my evaluation set may, for example, have 1,000 healthy samples and 1,000 ill samples, but in my population, the probability that somebody is ill may be very easily something that is very low. If I pick one person random, there is, in this case, 1 over 10,000 probability that is ill. This is not unreasonable. These are perfectly reasonable numbers. If you pick for some illness somebody at random, the chance that is ill is usually very low for that illness. So my evaluation set will have an empirical prior that does not reflect the reality over which I am employing my data set, my classifier. If I use an error rate measured on this data set, it will not be a good proxy for the number of errors that I would have in real use cases. So, as we said, it does not account for the fact that errors are different. It relies on the empirical prior of the evaluation set, which may not be the same as the application prior. Finally, one last thing, this is slightly less important, but still is interesting on its own. It's unnormalized. What does it mean? It means that if I tell you 90% accuracy, that's not really telling you anything about my system. Well, it's telling you something on how good I solve the problem, but it's not telling you anything on how good my system is at solving the problem with respect to other options. In which sense? In the sense that, let's make it with a slightly different example. In the slides you have to do with 90, but a classifier that does 99%, would you consider it good or not accuracy? On what?
On the data sets. Because if the model always predicts one class and 99% of the samples are of one class, of that one class, it will have 99% of accuracy, but it's just
Yes. Okay, so your colleague gave the answer already. The issue is if that while 99% allows me, and we will go back to these slides in a moment, while 99% of accuracy for many tasks is good in the sense that a classifier that does 99% is almost always correct. So we see in many tasks this is a good level. It may be a good level, but it may be worse than not using my classifier at all. Why? Because we will see we may have a classifier that makes its decision without even looking at your feature vectors. We see that it's a classifier that employs just prior information, that essentially will predict all samples as belonging to one class. They will have a higher accuracy. For example, we have, on the slides, we have this example, is a weather prediction problem. We have two classes, rain and clear. This is in a dry place where it rains, where it doesn't rain a lot. You can see that here I have that my classifier predicts rain 15 days when it's actually rainy. Then 30 days it predicts rain and it was clear. It predicts clear, but it was raining 20 times, and 300 times it predicts clear and it's clear. If I compute accuracy, I measure 86%. So that means that only 1 day out of 6, I'm giving the wrong answer. But as your colleague said, let's imagine now a classifier that always predicts clear. If my classifier says clear every time, what do I get? Well, I get 0 here. I never predict clear. Then what I get? That 35 days I predict clear and it was rainy. The number of rainy days is the sum of these two values. It's 15 plus 20. Those were the rainy days in my dataset. The number of clear days are 330. So I predict clear correctly 330. I measure my accuracy. That's 330 out of 365, 90%. So if I don't use my classifier, I get the correct answer more often. So my classifier, the 86%, on its own is telling us something, how many times I will get the correct answer, but it's not telling us whether it's actually a classifier that is useful or not, in the sense that we can't, just by looking at 86%, know whether the classifier is actually able to extract information from the data, or, like in this case, is doing worse than if we didn't even use the classifier at all. Without using the classifier at all, we can just obtain 90%. And we will see that this 90% essentially corresponds to a classifier that employs the class prior alone to make what are called optimal decisions. So we will see that it's trivial. No, it's not trivial, but we see that it's easy to build let's call it dummy classifier that will essentially base its decision just on the prior, on the class prior, then I don't need to use any model for the features because I will not even look at the features. And if that classifier performs better than my recognizer, my classifier, then my classifier is not just not working well, it's actually harmful. So it works worse than not using it. In this sense, we will see a way to normalize our error rates so that the values that we get already tells us whether the classifier is useful, so it works better than such a dummy classifier that doesn't even look at the data, or not. So these are the three things. The last, as I said, it's important on its own, but also the non-normalized version of the matrix gives us other information, gives us the amount of errors that I make in the case of accuracy. So normalization is important, but sometimes I may not want it depending on the task. But the first two are essential because we don't want to treat all errors in the same way, and we don't want that the metric reflects the evaluation empirical prior. We want it to reflect the application prior. Questions up to here? Now, yes. The answer is no. We should use a metric that takes that into account, and why not? Because we said it last time. Imagine you have proportion where 1 ill to 10,000 healthy. And then I want 1,000 ill in my data set. That means that I need to collect 10 million healthy patient information. Now, 1,000, if I'm in hospital illness, it's easy to collect. But to collect the data of 10 million people, you will need to take Italy and take 1 person out of 6. So that's probably not a convenient way of doing it. So TBA, my dataset, my evaluation dataset will not have the same prior as the application because it's just not feasible. And then what happens if I want to see what would happen in different applications? I would have to start throwing away. So, for example, I would like to know what happens if the probability of illness is 0.01. What happens if the probability of illness is 0.1? What if the probability of illness is 0.05? Because these may be different scenarios. For example, I may have different regions where the prior probability is different because of the population. Do I want to collect 3 different data sets with different proportions, or take the same data set and throw away random samples? Then I'm not even basing results on the same data set anymore. Well, I could, but in any case, I would have to collect the data set for the worst case and then start to throw away samples. And throwing away samples is never a good idea. If I have samples and the best thing I can do to use them is throw them away, then I'm not probably doing the best thing. I collected them. If I am able to use them, I would be better. So the answer is, even if I decide to go this route, once I have these 10 millions, why should I use just 5 millions because my prior is different? Wouldn't it be better if I were be able to use all the 10 million information and use it in a proper way? So to simulate this condition. So the answer is, that's what I want to avoid. The whole reason here is I want to avoid exactly collecting a data set that mimics the application prior, because it's usually not feasible, and because I may want to consider many different prior probabilities for many different scenarios at once, and not base my results on collecting several different instances of the data set. So what we will see is we will take our data and properly weight them. That's something general. I mean, you may have, if you did other courses, you may have been told that to make your data set balanced, you can oversample, undersample, but those kind of things, in my opinion, are always wrong, because when you oversample, you're just creating new instances of your data. When you undersample, you're doing even worse. You're throwing away information that you have. So the correct way is to understand how to weight the classes properly in order to use all the information that you have without throwing away anything. We'll see that when we do other models. For the generative ones, the problem is not there, but we will see this problem when we discuss logistic regression and super vector machines. And there we will discuss that you don't want to throw away. So oversampling is essentially useless because you're generating new data that is the same as the ones that you have. So you're not injecting information. It's just a matter of properly weighting your data, your samples, and then you can simulate them. Undersampling is even worse because you're throwing away samples. So the correct answer to undersampling is I don't throw samples. If I need, I weight them less than 1. And we will see how to do that. But we will see it after the holidays. Okay, so the idea here is whenever we have data, we want to be free to collect the data that we are comfortable with. So for example, balance evaluation set with few thousand examples for each class, and then we want to be able to simulate different applications with different priors. So we'll see how to do that. Okay. Other questions? Okay. Now, we have up to the moment said that we measure our results on our evaluation set. Let's be a bit more, let's understand better what we're doing when we do this. Well, what is our goal? Well, our goal is to have performance that is optimal for the application. That is, considering the field where we will run our classifier, we want our classifier to optimal for that application. And we would like also to predict how such classifier, an optimal one or even a not optimal one, would perform on application data. Now, unfortunately, measuring the performance on the application data is not possible. It's not possible before we actually have classified the data and have retrieved the real label of the data that we classified. Notice that the second step may not even be possible. I may never have the real label for the data that I want to classify. I will not, if I'm using it to make a diagnostic system, I will never know if the patient was really ill or not, well, unless the patient dies, but maybe I don't treat him and he was ill, but it recovers on his own. So I will never know that he was actually ill. I will not have the real label. And in any case, if I have the real label, I assume that I will have after I have used my classifier, because otherwise I would not need my classifier at all. If I have the label for the samples, why should I use the classifier? Which means that we can't say in advance how well our classifier will be on application data. That's just something we can't say. We will never be able to say it will do exactly this amount of errors. What we can do is try to simulate. That's the same. That's the same thing that we do during training. We don't have access to the evaluation data we want to classify, but the training data tries to simulate that. Here we have something similar. We want to predict how well we will do on application data. We can't do that for application data, but we can run a simulation to get what is called an estimate of our performance. Now, the estimate is what we compute on the evaluation data. And we will see that we can give two interpretations. Now, probably we will not need to go into the details of the two interpretations, but what are the interpretations of the evaluation matrix? One is they are a measure that is exact for our performance on the evaluation set, because on the evaluation set we are measuring exactly how good the metric would be for those data if we had applied the classifier to those data, if those data were the real application. In any case, sorry, remove the last part. Exactly on those data. So if we apply our classifier to those data, we measure exactly what is the performance for that dataset. And that's one thing. And then we can use this as an estimate, but we need to remember that in this case it's just an estimate of the performance on application data. Hoping that the application data behaves similar to the evaluation set, which is always a hope because we have no guarantee that our evaluation set is actually representative of the application. We hope for that. As always, when we train a model, we hope that the training data is well matched to the application data. If it's not, then all considerations that we do will not hold. But under the assumption that they behave in the same data, then they behave in the same way, we'll use the metric computed on the evaluation set as an estimate of how well the model will perform. Being an estimate means that it's also something that is not 100% accurate. That is, it will not tell me how the model exactly performs on application data. We'll not go into the details of this because, again, it would open too long parentheses, but remember that there are these two ways of interpreting the same value. Exact performance on that specific data and estimate of our performance on application data. Now, for the first one, well, okay, nothing. Let's move next. No, sorry. Okay. Okay. Now, in the next slide, you have, remember that I skipped here to make the example of why accuracy was not normalized. Now, to see also how to overcome the other problems, so to address the non-normalization, well, we discussed already the fact that it's not normalized, so the values itself doesn't tell us whether the classifier is useful or not. Then we said, we need to take into account the fact that different errors have different costs, and if you have seen before, I already started drawing a matrix like a table where I said predict healthy, ill, and actual label healthy, ill. And then we said from this we can see that there are two kinds of errors. And then we said also we want the model to depend on the application, on the prior probability, but the application prior, not the empirical set prior. We see that this also can be obtained by looking at all combinations that we can have of predicted and actual label. That is, for any classifier, to see how to get to a single measure, we first start from what is called a confusion matrix. That is a matrix that contains all possible outcome combinations for our system. Let's imagine we have k classes, then our model can predict one out of k values. Then each sample may belong to one of the k classes. I have my evaluation set samples, x1 with class 1, x2 with class 2, x3 with class 3, x4 with class 4, etc. I run my system and I get a predicted label for each of these one. For example, let's go back to the binary problem. Then if it's multiclass, it's the same. Healthy, healthy, ill, ill. And then my prediction may be something like this. Now, I can count for each class, and each prediction, so for each combination of these two, I can count how many times I get that combination. So for example, how many times I predict class C1 for samples of class C1. If you want, how many healthy patients are predicted as healthy, the first one in this case. And I can repeat for all combinations. So for each class C1, for each class C and prediction P, I will have a combination. The sample is from class C and it was predicted as P. I count how many times this happens and I fill this table, this matrix, with all these values. This is called confusion matrix. For each combination of class label and predicted label, I have the number of samples that I have that belong to that combination. So in this case, in our case, we have one healthy, one label healthy and predicted as ill, so it will be here, one label ill predicted as healthy, and one label ill predicted as ill. Now, the diagonal of this matrix contains what? These are the samples that, for each class, are predicted from the same class. So the sum of these values is the number of correctly classified samples, while all the others are incorrectly classified. So on the diagonal, I have correct classifications. Outside of the diagonal, I have wrong classifications. So we already see that the error rate can already be computed by this. Or let's with the accuracy, but then we will move to error rate. The accuracy is the sum of the elements on the diagonal divided the sum of all the elements. Elements on the diagonal are the correct one, the others are all. And the error rate is the sum of the elements out of the diagonal divided the sum of all the elements of this matrix. Remember that the sum of the elements of this matrix is exactly the number of samples in my dataset. Here I have all the combinations that a sample can belong to. We also observe that another information that we can take from the matrix is the number of samples of each class. If I sum the columns of each class, that corresponds to the number of samples of that class. So I can compute, let me just see. I can compute additional information that is, for example, the number of errors that I make for samples of each class on its own. So I can consider, for example, class C1 and ask myself, if I restrict myself to sample of C1, how many times I get the correct answer for those samples and how many times I get it wrong? Well, the number of samples of C1 is the sum of the column. This is the number of correct classification of C1. This divided by the sum of the column is the number of correct, is the percentage of the fraction of correct assignments for samples of class C1. Now, before we see how to derive which informations we can derive that are useful for us, let's go back to the binary case, because we will see that the binary case, for the binary case, we can specialize some of the things that we say in a much deeper way. So for a binary problem, it's interesting to observe what are the four outcomes, because for binary problems, these typically have specific names. For binary problems, essentially, we have two labels. We said that we will call one false and the other true class. So for example, this may be an answer to the question, is the patient ill? True means it's ill, false means he's healthy. So true and false are typically the answer to this kind of questions. And then what I have, I can say that a sample is from class F and I predict, well, I can have a sample from class false and predict it as false. This will be called true negative. Negative because this is the prediction, so the second term of these labels refers to the prediction that I made, and true tells me whether the prediction is correct or not. Now, I don't like this way of naming things because I find that it's just making confusions, because we need to remember that this The second part refers to the prediction, and the first part does not refer to the class, but whether the prediction was correct or not. So I don't like this way of naming because I think it makes confusion, but that's a standard naming that you find everywhere, so we have to stick with this way of calling the different terms. So, true negative, I predict as negative and I'm correct. False negative, I predict as negative, but I'm wrong because the sample was from the true class. So it's negative prediction, but it's false negative, it's not correct. False positive, I predict as positive, but the sample is from the false class, so this is not really a positive sample, it's a sample that was actually from the negative class. And true positive, I predict as positive, and it's correct. Now, true positive and true negatives are the correctly classified samples, while the other two are the incorrectly classified. From the data matrix, we see that in this case, accuracy and error rate, as we said, are what? The accuracy is the sum of the elements on the diagonal divided all the elements of the matrix. On the diagonal, I have true negative and true positive, and the rest is the sum of all the terms. That's exactly what we said before. And error rate is obtained in the same way, taking the misclassifications divided by the number of samples. Now, as we started, okay, this was the example that we said before on why normalization is important. Let me see. Let's do like this. Okay. And we said why error rate and accuracy are not correct. We'll see how to specialize this for multi-class, but let's now concentrate on binary because that's easier to understand. So let's restrict ourselves to binary problem and see how we can, at least for a binary classifier, address those problems that we have discussed before. We'll do it in a way that is, I hope, intuitive at the beginning, and then we will show, so I will give an intuitive reason for that, and then we will show that it's actually a well-defined quantity that has some interesting properties. That is, we will define that as a way to measure performance that allows us to say that if when we go back to decisions, will allow us to prove that our decisions are indeed optimal. But let's start with the intuitive way. To start with the intuitive way, we said that we have two problems. We want to take into account the application rather than the empirical set prior, and we want to be able to introduce costs of different errors. Now, if we look at the error rate, it's not clear from these expressions how to do this. From this expression, it's not clear directly how to do it. So let's rewrite these expressions by introducing additional measures, such as the one that I was telling before, the error rate per class, that will allow us to express both accuracy, or better, we will focus on the error rate. The error rate in a way that will suggest us how we can deal with different application priors. We said, let's go back to the matrix of true negative and true positive, etc. So we have predicted false, predicted true, label false, label true. Then we have false, false is a true negative. This is false negative. This is false positive and true positive. If I'm not mistaken, as I said, I don't like this naming because it's negative. Yes. Yes. Also, I don't like this naming because in the field that I work in, we use different namings to avoid these issues altogether, but that's not what you would find in books. Actually, you have it in the slide, how we call it in different, no, sorry, not this one. These two are of interest for us. Now, we said if we consider each class on its own, we can compute accuracies and error rate per class. So we can say, let's look at the sample from the false class. How many times I make mistakes for these samples? Well, it's false positive divided number of samples of the false class. This is called false positive rate, the rate of false positive. We call it also false acceptance. Why? Because if this was a biometric identification system, a false positive is somebody who you admit inside the system because it passes the verification step, but it should not be accepted. So it's as if somebody took your phone, put his finger on your fingerprint scanner and got access to the phone. That's a false acceptance. It's an acceptance. The system accepts the fingerprint, but it's wrong because it should have not been accepted. We can repeat it for the other class. For the true class, we can compute the number of errors, false negative, divided the samples of the true class. This is called false negative rate. And again, in biometrics, it's called false rejection or miss rate. False rejection because, again, you put your finger on your phone and the phone doesn't unlock because it doesn't recognize your finger. So it rejects you even though it should have not. Apart from this, that are just different ways of naming it, these are essentially an error rate for the positive class and for the negative class. Of course, if I have a multi-class problem, I can extend this to all the classes. For each class, I can compute the corresponding error rate. Then you may have seen in other courses what are called true positive rate and true negative rate, which are nothing else than the false positive and false negative rate inverted. So rather than counting the errors, I count the number of correct predictions for each class. It's the same information, and we will work with these two rates, but this is the same information. Once you know the one, you know automatically the other. Just one minus gives you the other. So there is no difference in the information that you have there. Now, we observe that these metrics already on themselves are independent on the dataset prior. What do you mean? What do I mean? I mean that the empirical prior corresponds to what? To the ratio of the different classes in my dataset. So for example, if I have 1,000 samples from the true class and 100 for the false, there will be an empirical prior of, let's do it the opposite. Let's make 100 and 1,000. Because the empirical prior is usually for the true class, and I want it to be small. 100 divided 100, 1,000. 100 divided 1,100. But do I need to know the number of samples of the classes of the other class to compute these pattern values? I mean, if I have the same true negative rate and false positive rate, but now I have 100 times more false samples, what do I have? Well, if the number of mistakes I make for a class is, I assume, independent on the number of samples, my rates will be the same. So I can imagine that for samples of one class, the percentage of mistakes I make for that class does not depend on the number of samples that I have on that class. Remember that each sample is evaluated, labeled on its own. So the prediction that I make for one sample do not depend on predictions I made on previous samples. So I can imagine that it's reasonable to imagine that if I take samples of one class, if I have enough samples of that class, then my false negative rate will not significantly change if I collect even more samples of that class and I measure the performance. You can imagine that if I have over 1,000 samples, I have 100 errors. If I collect 10,000 samples, I will probably have something around 1,000 errors. But this holds for one class. To say this, we didn't need to know how many samples I have for the other class. For the other class, I may have one, I may have 1 billion. It doesn't change how I measure the error rate of that class. So the false positive and false negative rate do not depend on the proportion of the classes in the dataset. To measure one, we just need to know how many samples we have of that class. We don't care of how many samples we have for the other class. The error rate is not like that. The error rate takes into account all elements of the matrix together. The denominator and the numerator both depends on all the classes. So these two quantities on their own allow us to give us metrics that are class dependent but do not depend on the empirical prior of the dataset. They just depend on the samples of each class considered on its own, ignoring what are the other classes. Now, the empirical prior, on the other hand, we said represents, well, for a binary problem, is the fraction of samples of class 1. For a multi-class problem, we have prior probability for each class. They must sum up to 1. They represent, the empirical prior represents what? The fraction of samples in the data set for that class. Remember, when it's empirical prior, it's the fraction of samples. Prior on its own is my prior knowledge on the data. The empirical prior refers to the prior computed exactly of those data as if they were all and only the data that exist. So in that case, it's exactly the fraction of samples. So the empirical prior of the dataset can be written in this way. Why? Let's go back to our matrix. False, sorry, true, negative. False negative, false positive, and true positive. How do I compute the empirical prior? The empirical prior is what? Sorry, F and T. We said that if this is the data set that we classified, it's the ratio of samples from class true with respect to the number of samples of the data set. How can I compute the number of samples of class true? The number of samples of class true is this column. These columns, the sum of these elements is the number of samples of class true. These are the samples of class true. Then some of them will be predicted as false. Some of them will be predicted as true. Altogether, they are the samples of class true. So this column is the samples of class true. And the denominator is the sum of all the elements. This is exactly how you would compute the empirical prior for this dataset. Samples of class true divided number of samples. So proportions of samples of class true. Now, let's rewrite the error rate using the putting in evidence the empirical prior. We can rewrite the error rate in this way. We split the numerator in two. So we have a sum at the numerator, so we split it into two fractions. Then for each fraction, we do what? Here, we multiply and divide by Tn plus Fp divided Tn plus Fp. This is what? Number of samples from class false. And on the other side, we multiply by Tp plus Fn divided Tp plus Fn. This one. So these are the number of samples from class true. Then we arrange our computation and we can write our error rate in this way. What did we do here? Well, let's look at the second term. What is this term here? True positive plus false negative divided all the numbers of the class, all the elements of the data set. What is? This is exactly the empirical prior. What is this term? False negative divided true positive plus false negative. What is this one? Go back one slide. It's false negative divided true positive plus false negative. It's the false negative rate. So this term here is the false negative rate times the empirical prior. If you prefer, let's call it and false negative of the true class. This is what? This is the false positive rate times the empirical prior of the false class, which is 1 minus the empirical prior. The prior for the false class in binary problem is 1 minus the prior of the true class. So we can see that it's a weighted sum of the error rates of each class, where the weight is exactly the empirical prior. How can I read it? Well, in a, again, frequentist approach, what is the probability of false negative? The probability of false negative is the probability that I predict negative when the label is true, and then the empirical prior is the probability that the label is true. While the other is the probability that I predict true when the label is false times the prior probability that the label is false. This is the joint probability of predicting false, let's use false, not and, false and label being true, and predicting true and label being false. So that's the probability that I have one error in my dataset. If I express it in this way, I can see that I can express it as a conditional per class error rate, where the conditional error rate is the false negative rate and false positive rate for the two classes, which with a frequentist interpretation, we can interpret them. Notice that when we do this interpretation, we are not using them as measure for the empirical data. We're treating these as estimates of probabilities. But in the frequentist world, a frequency is exactly an estimate of a probability. That's how we define probabilities, actually. The frequency of an infinite number of repeated experiments. So this would be the probability that I get a wrong answer for samples of class true. This is the probability that I get a wrong answer for samples of class false, each weighted by the probability that a sample belongs to that class. That gives me exactly my error rate. The probability that I make a mistake given that it's true times the probability that it's true. That's the probability that a point is true and I classify it as false. The second is the probability that a point is false and I classify it as true. And the sum is, since these two are exclusive, the sum is the error rate, the probability that a sample is classified incorrectly. But now that we have this, I hope that it will not cause problems if now, rather than using this, we define a new error rate for an empirical application prior that employs the same expression, but where the prior probability here is replaced by the application prior. So what are we doing here? We are simulating a data set where the false negative and false positive rate are the same as our evaluation data set. But the prior probabilities for the two classes are not the same. So essentially, how do we address, and we will come to this again, how do we address the fact that our empirical prior do not reflect the application prior? We use our data set to get an estimate of these two quantities, and then we treat this as if they were the probabilities of the two kinds of errors for a different data set, which has these proportions for the data. So we essentially simulate as if we had a data set where the application prior is the data set prior. We never create this data set. We assume that there is such a data set which has the same false and negative probability rates of the actual evaluation set that we use. So essentially, we estimate these quantities that are independent from the empirical prior, so we can treat them as if they were also the numbers that we would have if we had built a dataset that has the application prior as empirical, but we will never do that. We will just extract this quantity from a different dataset, and then we'll combine it with the prior that reflects, that simulates our application. And in this way, we get an error rate that reflects our application. We will also prove this. So now this is the intuition. We will show this with, we give this in a bit more mathematical context, but this is the idea. And to finalize the idea, to take into account costs, this is what? This is the probability that I make a mistake where I label as true and the label is false. Now, if these mistakes cost more than the other mistakes, I will multiply this probability by a cost. This will give me what is called an expected cost. So the cost that I expect to pay based on the errors that the classifier makes when the false positive rate and false negative rates are those that I measure on my evaluation set, where the empirical the prior is the application prior, and the cost of the different errors is defined by whoever wants to measure the performance. Of course, the cost is not us to decide. It's not us who make the diagnostic system who need to decide whether how it's expensive to let a patient die or not, or treat him if it doesn't need it. That's up to some doctor to decide how stressful it is for the person, the treatment, how high is the risk that he will actually die, so it's actually a cost for the person or not. So we assume that these costs are given, and then we will define this expected cost that essentially will take this expression and extend it to also include the cost of the different kind of errors that we can have. Questions? Okay. Now, just to finish before the break, let's go back to this example, because this example will, well, maybe this example I will skip. Let me just see. Okay, let's make now 10 minutes break, and then we will see. Let's make 10 minutes break now. Okay, now let's resume. As somebody asked before during the break, yes, there are other metrics. For example, you may have seen precisions or other metrics where essentially you take your prediction matrix and you compute metrics by normalizing with respect to the predicted samples for each class. So grouping samples by predictions rather than by class label. Why don't we treat them here? Because essentially they suffer with the same problem as accuracy. They depend on the empirical class prior. So they are not able to give us those quality that we wanted from our matrix. So we will not consider them here because they will not meet our desires. Now, before we formalize how to derive a metric that works for both binary and multi-class problems, let's start with an example, because you may ask, one question that you may have is, let me see if I can find the example. But why do I need to do this? Okay, we said we want to measure how good the model would be on different data sets, but if we are just interested in comparing the models, wouldn't be something like looking at the accuracy of the different models be enough to decide which model to take? Maybe we are not interested to know exactly how the model would perform on our application data. Then do we need to take into account the application prior, the cost of errors, and so on? Couldn't we just look at the accuracy and say, the more accurate model is the model that we will select to use for our task? And the answer, of course, is not. And to see why it's not, we will see it with an example. We see that as we change the class prior and as we change the cost of errors, we have two competing systems, and depending on the prior information and the cost of errors, we will end up choosing different system as the best one. The example is again the health prediction, the diagnostic system, and imagine that we have a data set with 1,000 negative and 1,000 positive samples, so true class and false class. And I have two classifiers, R1 and R2, that I run on this evaluation set. And I'm using this evaluation set to decide whether, in practice, I should use R1 for my patients or R2. Now, if I look at accuracy, what do I have? For this model here, let's look at error rate. It's easier to compute. The error rate is what? Well, here I have 80 errors out of 2,000 classes, 4% error rate. Here I have 60 errors out of 2,000 samples, error rate 3%. So according to error rate and accuracy, I would select R2 as my classifier. However, let's now apply our reasoning, the intuition we had before on how to incorporate application prior. So we said if our application has the same prior as the empirical prior, in this case the empirical prior is 0.5 because we have 1,000 samples from the true class and 1,000 from the false class. For an application which has exactly this empirical prior, if we replace the empirical prior with the application prior, we would obtain exactly the same error rate. So for an application where the prior and not the empirical prior, the prior is 0.5, this reflects the error rate that we would have on that application. So we would select R2. But now let's imagine an application where the prior is different. Prior for class 1, now I don't remember if class 1 is healthy or negative, so class 1 is ill, is the exam is positive, so you have the illness. That's what usual medical exams tell you. When it's positive, it's not a good thing. So the exam is positive, you are ill. The prior probability of being ill is just 1%. So if somebody takes the exam, we know that 1 out of 100 are positive. The others are not. Now, what is the error rate that I would have for my classifier? If I replace the per class error rate and I use this prior, I recompute the error rate, what do I have? Well, we need to use the expression. It's false negative rate times prior, so it's false negative rate times prior, plus false positive rate times 1 minus prior. False positive rate and false negative rate are the same as we computed before, when we computed accuracy and error rate. But now we need to combine them by prior. In this case, R1 will be better. Why? Because if we look at the confusion matrix, R1 does fewer errors for the negative samples. The vast majority of the people belongs to the negative samples, so the vast majority of the times I will have a sample for the negative class. For that class, the classifier is more accurate. So overall, since the people that are ill are very few, the number of errors that I make in total is smaller. If the cost of the errors is the same, so it doesn't matter, both errors have the same cost for me, then it's better to use the second, because I will pay this cost only if both errors have the same cost, C, I will pay this cost only 2% of the times, while with the second classifier, I would pay that cost almost 4%. We see when we have introduced cost properly, that once we introduce costs that make sending home somebody who is ill more expensive than treating somebody who is healthy, things will change again. So depending on the cost and on the application prior, which system is better changes. So we can't use the accuracy to decide which system to use. The decision should be based on the specific task that we will want to solve. So we need to take into account the application prior and the cost of errors to decide which system we want to use. Not just to measure how good it would be on that task, but also when we compare systems, we need to do the comparison for a specific task to decide which would be better for that task. And things can change if I change the task. Okay, here we set everything. Now, of course, the method that we will find depends on the application prior. We already have intuitively said how. Essentially, we will simulate a dataset that has the application prior as prior by keeping fixed the per class error rates and changing the prior of the different classes. We will also introduce costs. Of course, it can be used to compare classifiers. The better, the lower it will be something that is akin to a cost. So the lower the cost, the better the classifier. And we will see how to normalize it so that we already, by looking at the number, well, for the unnormalized one, we can know what is the cost that we will pay because of the mistakes we make. For the normalized one, it will tell us whether the classifier, how much the classifier is better with respect to a dummy classifier. So what is the relative cost with respect to you not using the classifier at all? Now, to derive all this information, let's start with some definition, introducing some formulas that you all like. We start with go back and defining what we want to solve when we solve a classification problem. We will introduce the problem in a slightly more general way, then we will go back to the standard classification problem, but we generalize it a bit more because whatever we say now can be applied to a broader context of tasks. So when we solve a classification problem, up to now we said we have a samples and we want to give it a label. The label of the class it belongs to. Actually, that's not the real story. When we run a classification problem, what we want to do is to decide what to do based on the samples that we receive, which does not necessarily mean that we want to label the samples. For example, imagine it's a weather prediction problem when I can have rain, snow, and sun. My task may not just label rain, snow, and sun, but decide should I take the umbrella or not. So this is my goal. These are the class labels, but my goal is to decide whether I should take the umbrella or not. So in general, we can generalize the problem as we want to take some decision that is some action inside a set of possible actions, taking the umbrella or not, and each action will have a cost that depends on the class the sample belongs to. So for example, I may say, if I take the umbrella, then taking the umbrella is the cost that I need to bring it with me. So if it's raining, if it's sunny, I have a cost, the inconvenience of bringing with me the umbrella, and then I have the inconvenience of bringing with me the umbrella even if it's raining or snowing. It may even be larger because then I will have a wet umbrella with me. But the cost of not taking the umbrella, well, if it's sunny, it's 0. Maybe if it's snow, it's 10. And if it's rainy, it's 10. If it's snowy, it's, let's say, 6. What does it mean? That if it's snow, it's less inconvenient than if it's rain. If it's rain, it's much more inconvenient if I don't take it than if I take it. In any case, I can, for each combination of positive class label and action, I can define a cost of the corresponding action given the label of the sample. Here the sample is tomorrow's weather. So I need to predict tomorrow's weather. I will have some feature vector that represents some quantity that I want to predict. My classifier will give me some information that then I need to use to make my decision. And my decision, the cost of my decision will depend on what is the real label of tomorrow. Is it rainy, snowy, or sunny? And the action that I choose. So if I choose to take the umbrella, if it's raining, for me it's a cost 1.5 something, some unitary cost. Here the unitary cost is bringing with me the umbrella when it's sun. Of course, cost can be euros. They can also be relative cost to some standard action that has a cost of 1. For example, if it's the ill treating patient, I may have different treatments. Each treatment will have a monetary cost as well. So that, in that case, the cost can be costs in euros that I have to decide which treatment I should give to the patient if I have several options for treatments. In other cases, it's just a convention. I say 1 is the cost of bringing with me the umbrella when it's sunny, and I try to estimate a relative cost with respect to that 1. In any case, this is a cost matrix that for each action gives me the cost when the samples that we are considering is from class K. Now, for us, we have the simplified model where actions are themselves classes. So assign the label A to a sample is an example of action, and in this case the set of actions corresponds with the set of labels. That's what we did up to now, but in general whatever we say now can be considered in a broader sense. I have different sets of actions with respect to the set of labels. We'll not see examples of this in practice, but know that whatever we say now is not restricted to have the set of labels of actions equal to the set of labels. This is not necessarily true. So for every action that we can take, we have the cost of deciding to take action A when the sample is from class K. Now, let's imagine we have a classifier, the classifier that we want to evaluate. The classifier R, we use R for recognizer because we will use C for cost, otherwise there will be too many C. If we have C for cost, C for classifier, there will be C for class, there will be too many C's. So here we use R for the classifier. How do we remember? A recognizer. Rather than classifier, today we will call it recognizer. It's to recognize the label. We have a recognizer. A recognizer is nothing else than a function that, given a sample, gives us a decision. For us, the decision up to now was the class label, predicted by taking maximum posteriori for the class, so the maximum class posterior probability. But in general, a classifier is something that, given a sample, will give me an action to undertake. The action can be just a label if the action set corresponds to the label set, or can be any action. So for example, I give tomorrow measurements of humidity, temperature, and so on, and the classifier tells me tomorrow take the umbrella. So in this case, the action is not the action does not correspond to the labels, but the classifier gives me an action for a feature vector x. So for a sample x, I have a function that gives me the decision that the classifier makes for sample x. And then, of course, for each sample, I have a label that is the class label of that sample, that is C. For the moment, we are talking in theory, so we may not have access to this quantity, but we assume that each sample has a class label. We have a sample vector, and for each sample, the classifier gives us a decision, that is an action, or if you prefer, in the simplified view of things, a predicted label for the sample, and the sample is actually of class C. If we know class C, we can measure the cost of the decision of our classifier. Remember that for each action, we have cost of action when the class is K. Then for sample X, the action that we take is action of X according to the recognizer. The class is C because we know that the sample is from class C. We go with these two entries in our matrix of cost. So for example, take umbrella and snowy. In this case, it will be the cost that we had in our matrix, which, if I remember right, for take umbrella and snowy was 1.5. So if the actions are labeled, then it's the cost of predicting this label A of X when the class label is actually C. But again, here we try to be a bit more general. The actions may also be, well, when we need to specialize, we will also only consider the case where actions are predicted labels, but what we say can be always considered in an extended way. Now, how we measure how good is our classifier? We can imagine that, well, what we want to see is, okay, we have a classifier, we have that if sample is X, then the classifier will predict A of X given R, and the cost will be the cost of the action given the class. And I said cost of the action given the class. Remember that even when we have predictions, predicting the correct class may have cost. Or we will see that it's not necessary. True that we can define a problem where predicting the correct class is always zero cost, but in general, I have a cost matrix that defines all the costs that I want to measure. Now, how do I evaluate what is the performance of my classifier? Well, if making a classification has a cost, so given a sample X, this is the cost that I will pay for my sample X from class C. This is the cost that I will pay if I use my classifier. I can try to measure what is the cost that I will pay if I apply my classifier to application data that is drawn from the application population. So ideally, what do I want to do? I want to evaluate, if I use my classifier on application data, what is the average cost that I will pay for my application. So I can imagine that I will, let's reason in a frequentist way. What am I interested into? Well, I will run my classifier on the application data. So I will, for lots of samples, compute the application samples, the tests. I will compute the actions. For each of these samples, I will compute the corresponding action, I will predict. Then each of these samples will have a corresponding label, which we don't know, but they have a label. They belong to a class. We don't know, but they belong to a class. So when we make some actions, even if we don't know the class, we will pay a cost, we'll implicitly pay a cost that is the cost of making the action. Assume that we know that afterwards we can get the correct, which were the correct label, then we can measure exactly on those data what was the average cost. So we can take the cost that the classifier made for classifying our samples, this is not C, divided by the number of samples. This is the average cost that I would pay for the application data that I want to classify. Now, of course, the problem is that we don't have all this information. Not only that, we don't even know what are the application data in advance, but we want to have a method that tells us how good the classifier would be on application data. So we define a metric that we will see we will not be able to measure, and then we will see how to use an evaluation set to approximate the metric, but we can, in any case, define the metric. How? Here we were taking an average over the application data. What is in terms of probability? We are computing the expected error when the expected cost, not the expected error, the expected cost of using our classifiers on samples that are drawn from the evaluation, from the application population. Or in general, we call it evaluation population as E. So sometimes we call it application, sometimes evaluation. When we say evaluation population, we refer to the population that we want to classify. When we refer to an evaluation set, when we use the word set, we mean a specific set of samples. Otherwise, application and evaluation populations are essentially the same thing. So we can imagine that our samples, the application samples that we want to apply our classifier on, are taken from some distribution that is the distribution of the real data that we want to classify. What we would like to compute is the expected cost of applying our classifier to this kind of data. Expectation is what? It's exactly, well, in the frequencies word is the average of applying my classifier to an infinite number of samples taken from the evaluation distribution. That's the definition of expectation in terms of the frequencies interpretation of probability. Now, the frequencies doesn't work here because we will not have we can't define, we don't even know this distribution, but that's a different problem. The expectation is, would measure if we knew the distribution of the evaluation population, would measure if we were to get an infinite number of samples, what would be the average cost that we would pay for classifying those samples. And this looks like a reasonable metric. We need to decide which classifier to use. The classifier, well, and how good it is. We measure how expensive, what is the cost that we will incur if we use the classifier, and then that gives us an idea whether we want or not to use the classifier. Now, E is the evaluation population. We start giving E also another meaning. We call also E as an evaluator, somebody who knows the application data, so who has complete knowledge of the data. So we can see this as the distribution of the application data, or the distribution for the samples, as somebody who knows the application data would define for those samples. Why is this? We will see why this is important. Hopefully today, otherwise tomorrow, why the distinction is important. But we'll come back to this later. Now we don't have slides anymore. What happens? Okay. Now, the problem is we need to compute this bias risk, which has a big problem. We don't know this distribution because typically we don't know the application data distribution. The application data is data that we have never observed. We may have models for that that we made during training, but those are not the evaluation population distribution. Those are the distribution for the evaluation population according to our model. So our recognizer may define a distribution for the samples and class, but that's the distribution according to the recognizer. It's not the distribution according to somebody who knows the application data. It's the distribution according to somebody who has only the information that our classifier has. And these two are not necessarily the same. we will see how to deal with that. Before we see how to deal with that, let's decompose this risk in a way, let's write this risk in a way that highlights, again, the different things that we're interested in, essentially the prior class probability and the cost of errors per class, that are the quantities that we were using before. We see that what we did before is actually the same that we do now. An expectation is where we have a discrete and a continuous random variable, so we have to consider the joint density. For the discrete, we need to sum over the possible class label. For the continuous, the sample, we need to integrate with respect to the continuous random variable. And the definition of expectation is marginalize the products, so integrate and sum, in the case of the discrete, of the joint density times the things that I'm taking the expectation of. Remember, expectation, for example, expectation of x squared would be this. So this function here, weighted by the density, the likelihood for the values of x, all integrated over the real line. That's the definition of expectation, which, if this was a frequentist approach, this would correspond to an average if I take samples from x and I compute over an infinite number of samples these quantities as n goes to infinite. That's frequentist interpretation. But we don't need this now, we will use it later. Now, this is a joint probability. We can always express the joint as class conditional times prior, as always. Notice that this is the prior of according to E. So the prior that somebody who knows the real application puts. So it's the application prior, not the empirical dataset prior. It's the of some empirical dataset. It's the application prior. And this is what? This is a class conditional density, again, according to somebody who knows the distribution of the evaluation data, that we don't. But in any case, we will solve that in a moment. We can factorize this joint. Then, if I have this joint here as in this way, and of course, remember that these are given the evaluator. This first term does not depend on x, so I can bring it outside of the integral. I call it pi c. This is a discrete probability. So I have a value of the probability for each class. So for class C, small c, this value is pi c. That is the prior probability for the class C. Then I can rewrite my bias risk in this way. It's a sum over classes of a prior, application prior for class C, times this expression. This is what? This is the expected cost when samples are drawn from the distribution of x given C. So it's the expected cost that I have for samples of class C. I have samples of class C. Remember that this C here is blocked because this C appears twice. It's the C that is outside. Inside the cost is the cost of taking the action when I'm considering samples of class C. And here it's the same class C that I'm conditioning my density with respect to. So it's this C and this C are these two. So I have, for a single class, the cost of the actions that I make for samples of that class, and here the cost is always referred to that class because the class is fixed inside this integral now. And the density I'm integrating with respect to is the distribution of the samples of that class. This is the expected cost for errors of that class alone. So if I had errors of, if I have samples of class C, this is the expected cost that I pay for samples that belong to class C, small c. And the empirical bias risk is what? Well, it's exactly an average of the per class error rate. This is an expectation. Expectation, you can see it as an average. It's the average cost for errors of class C And then for each class, I reweight it by the probability that a sample is from that class. So if a sample is from class C, I will pay on average this cost. The total cost is an average of the per class average errors, where the second average is taken with respect to the class prior. So for example, if from class 1, my average cost is 1.5, and from class 2 is 2.5, and from class 3 is 4, and then prior probability for class 1 is 0.1, prior probability of 0.2 for class 2, and 0.7 for the last class, what is the average cost that I would pay? Well, on average, for samples of class 1, I pay 1.5. And how many times I see errors of this kind? 10% of the times. Then 20% of the times, I will pay an average cost that is 2.5. And then the other 70% of the times, I will pay an average cost for those samples of class 3 that is 4. So my overall average cost is the sum of these terms and whatever it gives. So we have put in evidence the role of the prior, which, as we said, we usually assume that it's known because we are estimating the problem, the risk for a given application. And we said when we decide the application, we assume that we have fixed the prior, so we know the prior. Then, of course, if the application prior is different from the prior that we used for our evaluation, our conclusions will not necessarily hold. We need our estimate for the application prior to be as close as possible to the real application prior, but that's a different problem. Here we assume that we are given a target application, so we know the application prior, because if we don't, then in any case we can't measure for a given application well, we can measure for a given application what would be the cost, but if we don't know what is our application, that's another problem. It's not that we are not able to measure how good is our classifier for the task, it's that we don't know what is our task. So we assume that the task is known, and now we have a term that is known. The other problem now is this part, the expected cost over the samples of each class. Why it's a problem? Because we don't know this distribution. This is the class conditional distribution for the evaluation population. However, now we introduce the role of our evaluation set. It's true that we don't have application data, but we imagine that we have at our disposal a set of samples that we call evaluation set that is taken from the same distribution of the evaluation population. So there are samples drawn from this class conditional distribution. And notice that I'm interested in the class conditional distribution. I don't really care at this point much about the prior probability of the empirical dataset, because that's been taken into account by the application prior already. What I need to simulate are the class conditional densities, not the joint densities. That is coherent with our goal. We don't want our metric to depend on the empirical dataset prior. So we want that our evaluation set are samples taken from the class conditional. We don't care that they are taken from the joint distribution, because in any case, the application prior will not be the same as the one that we use to create the evaluation set. But we can imagine that for each class, the samples are taken from the class conditional distribution of the application. Of course, this may not be true. If this is not true, our evaluations, our metrics will not reflect our application. But that's, as always, if we have no assumptions on what will happen in our application, we can make no prediction of what will happen when we use our system. We need at least some coherence between what we develop and what we will have in practice. Otherwise, we cannot say anything about the future if there is no relationship between the future and the past. Here we're always trying to predict the future, essentially. So we assume that the future behaves as the past, so the application data behaves as the evaluation data. Then we can replace this expectation by a weighted sum computed on the evaluation data. And this now holds true in the sense that as NC will go to infinite, this will approximate as well as possible the integral. So we can take the average cost computed over the evaluation set as a proxy, as an approximation of the class, of the per class cost that I would want to compute and that I can't compute because I don't have samples. I don't know the empirical class distribution. Sorry, the distribution for the evaluation data. So we replace the distribution by the empirical class distribution and approximate this integral by the summation. The summation is what? I sum over the samples of each class, so each time I'm considering a single class, what the expected cost of the actions taken for the samples of that class. This is similar, we will see it becomes exactly the same, as average, as computing a sort of per class error rate. Remember that when we were doing it intuitively, we said we compute per class error rate, and then we weight this per class error rates by the empirical prior. So we had some bit. We said we take the per class error rate and we weight it by the empirical prior. Now the cost will take the role of the error rate. So rather than having error rate, we have per class cost. And we will see that the per cost depends on the error rate per class. So when we finish developing the model, these terms will also appear back, because they are required to compute the average cost per class. But in any case, once we are able to compute the average cost per class, our metric will be this is the average cost per class computed on an evaluation set, approximated by that, and then weighted by the application prior. So we have overall empirical bias risk, average cost per class on the evaluation set. These averages are weighted by the class empirical prior and then summed all together. This gives me the average cost that I pay for a sample of the evaluation set. Again, this is exactly the empirical bias risk for the evaluation set. So if I assume that the evaluation set is the only thing that exists, and it's a proxy for the application bias risk when I assume that the quantities I'm not able to compute can be approximated by a finite sum over samples taken from the same distribution as the application data. So this as a proxy for the application error rate, application cost holds from how well this approximation holds. So of course, the more samples I have, the better the approximation of the integral with a finite sum, which is the reason why we need lots of samples to get a good estimate of the error rate. Now, this was called bias risk. The version that we employ here is called empirical bias risk because we replace the expectation over the samples distribution with the expectation over the empirical distribution of the evaluation set. So the empirical distribution of the evaluation set is used as a proxy for the distribution of the application data. What time is it? Okay, we still have time. Of course, lower cost is better performance. The lower we pay for using our classifier, the better it is. Now, how do we compute it practically? Well, we can give an example to see that it's harder to define than to actually compute. And to see what does it give, let's consider, let's try it with a 3-class problem. And let's define a cost matrix in this way. So we have 3 possible predictions, 3 possible labels. As I said, for the examples, we use a case where the labels and predictions are the same set. What are the costs? Well, here we have that the cost of correct predictions are all 0. Then if I predict class 1 and the classes, I don't know if it's all 1, 2, or 3, or 0, 1, 2. Let me just see. 1, 2, 3. So if I predict class 1 and the sample was from class 2, I pay 1. And if I predict class 1 and the sample was from class 3, I pay 2. So you see that the cost matrix encodes what? Well, imagine that class 1, 2, and 3 are 3 possible outcomes. If a sample from class 2 is predicted as either classes which are close, I pay 1. If a sample from class 1 is predicted as 3, which is far, I pay more than if I predict it as class 2. For example, you can imagine that cloud, rain, sun. Whatever the outcome, I can say that if it's cloud and I predict as rain or as sun, it's slightly less costly, the error, that if it's rain and I say it's sunny, the error is more expensive. So it's something like this where far classes have a higher cost, while for the one that is in between has a better, it's lower, gives me a lower cost if I make a mistake in that sense. Now let's imagine that these are the class prior probabilities. So this defines the application. For the 3 classes, these are the probabilities. We actually don't need the prior probabilities now, but we will need it in a moment. Let's imagine now that we have our evaluation set. On the evaluation set, we have, I don't know how many, the sum of these values, number of samples. We predict all of them, and then we build our confusion matrix. Confusion is what? Here is predict 1, 2, 3, and here is label 1, 2, and 3. So for example, 205 samples of class 1 are correctly predicted as class 1, while 50 samples of class 1 are incorrectly predicted as class 2. Now let's compute the error rate. Let's start with class 1. We have prior is 0.1, 0.3. Then, how many samples we have for the, we need to compute the average cost. So we need the sum of the cost divided the number of samples. How many samples do we have? The sum of these 3 values, which is 400 samples of class 1. Now, how much will I pay? Well, for samples of class 1, 205 are correctly classified. If I correctly classify samples of class 1, I pay 0. So for those samples, I pay 0. Then I have 145 samples, this one, that are classified as class 2, this one. These 145 are from class 1, but I predict them as class 2. So I will pay 1. Then I have 50 that are from class 1, and I predict as class 2. So I pay a cost 2. Cost is the sum of this cost. So these are the costs per sample. So I have 205 samples where the cost is 0, 145 samples where the cost is 1, and 50 samples where the cost is 2. Overall cost is the sum divided the number of samples is the average cost per class. Then I need to multiply by 0.3 because 30% of the samples will be actually from this class. So I take the average cost of samples of this class, and 30% of the times I will pay this cost on average for my samples. Then I can repeat it for the other classes. It's not difficult. Sample of class 2 are the sum of these, which is 402 according to the slides. Then we have 111, which are class 2 predicted as 1, pay 1. Then 199 pay 0. 92 I pay again 1. So overall, this is the per class cost, and then I multiply by the prior. I repeat it for the last class, and these are the 3 costs of each class. The empirical bias risk is the sum of the contributions of the 3 classes, so it's 0.559. So for example, if these were euros, 1 euro, 2 euro, and so on, this would actually be average cost for each sample, 0.559 euros. I pay 0 when I do the correct classification. Sometimes I'm wrong. On average, this is what I will pay because of my wrong predictions. Then, of course, if I charge somebody €1 for each token that I classify, I will have that each token gives me €1 and costs me 0.559 because of the errors that I make. So, of course, here I'm paying costs of using the classifier. So, of course, when I use the classifier, I have some gain that comes from somewhere from the fact that I'm using the classifier at all. So, but that's another, it's not of interest for us. This is the cost of my errors. It's stuck. Okay. So this is the empirical bias cost. Now let's see how it behaves for a binary problem. For a binary problem, we gave an intuitive result before. Now let's see if this corresponds to our intuitive result. So let's go back and consider a binary problem. In the binary problem, we have 4 possible combinations of prediction and label. Now, without loss of generality, we assume that correct classification costs 0. Why? Because if they don't cost 0, we can renormalize our costs so that correct classification costs 0, and the cost that we neglect is a cost that in any case we would have to pay regardless of what we predict. So essentially, we can always renormalize our costs so that the cost of the correct classification is assumed to be 0. So correct decisions have no cost, and we also assume that the cost of the errors are greater than 0. Again, we can show that this is not a limitation, but the reason we do is in this context because that's easier to understand. Of course, the bias cost is defined even if this is not true. We would just need to compute it. But let's assume that these are the costs because that simplifies the expressions that we have. And we could actually show that it's possible to go back to a problem where this is the matrix of costs and the problem is equivalent. We will not show it, but we can. Or if you don't want, you can use the full matrix of costs with the bias and error as we have defined it before. But since it's possible to go back to a configuration like this, we will focus on a problem where predictions, correct predictions that cost 0, and we have to cost for wrong classification. Now, since we have binary problems, essentially we have a cost for false positive. So we predict true when the point is from class false, and the cost of false negative, we predict false when the point was actually from class true. Now let's write our empirical bias risk for this cost matrix. The empirical bias risk is a sum over the samples of the 2 classes. So I have 2 classes, so the outer sum, I don't write it, I write explicitly the 2 terms of the sum. I have a contribution of class true and a contribution of class false. The contribution of class true is what? It's the prior times the average cost of the samples from class true. Sorry. This is exactly the contribution of the cost for the samples of class true. This CI star is what before we were calling action XIR. We call it CI star, the predicted label in this case. So the label is a prediction, we call it just CI star to simplify the notation, but it's the prediction made by our recognizer. And this is for the first class. This is the prior for the first class, and this is the average cost for samples of the first class. That's the empirical bias risk just rewritten for this specialized case. Now, what do I have? Well, let's bring this NT. Okay, this NT inside is not important. Let's look at this term. This is the cost that I pay for predictions made for the class true. What do I have? Well, whenever I predict as true, so if CI star is true, my cost is 0 because here we are considering sample of the class true. If my prediction is false, then the cost is what? Is the cost of a false negative. I predict as false and it's wrong. So negative, prediction is predicted false, and false negative because the prediction is wrong. So I have a cost of false negative that I pay only when the prediction is false, which is, let's skip this one. I have, every time my prediction is false, I have a false of cost negative. So let's bring this cost negative outside. What do I have? I have this summation is the cost of false negative a number of times equal to the number of wrong prediction. So I have pi t per times cost of false negatives times, I have 1 over nt outside times number of times where I have a false negative. Okay? So number of false negatives. The sum here is number of false negatives. Every time I have a false negative, I pay a cost of this kind. But this term here, number of samples of class true, number of false negatives divided number of samples of class true, we call it false negative rate times cost of false negatives times prior of class true. So for the class true, I pay what? A cost of false negative every time I have an error of that kind. On average, how many times I have an error of that kind? Well, remember the definition we gave, the interpretation we gave to this term, that's the probability of having a sample from class true times the probability that I make a mistake given that the sample is from class true. So this is the probability of a mistake of kind false negative. When the prior is this and the false negative rate is this, I need to multiply it by the cost of a false negative. This is the probability that I make a mistake of kind false negative, and this is the cost that I pay when I make that mistake. And the same for class true. I have the probability of a mistake of kind false positive times the cost of that mistake. And the probability of a mistake of a kind false positive is probability that I have a sample from class false times the probability that a sample from class false is mistaken as a sample of class true. Overall, this is the average number of errors of that kind. I multiply it by the cost. This is the average cost that I pay for my classifiers. This is exactly the empirical bias risk. So what we introduced before the break, we said we will need to account for the cost of errors. We just need to weight each error by the corresponding cost, and this corresponds exactly to the empirical bias risk that we have seen is a measure of the error that I make on my evaluation set, and as long as the integral approximation with the sum holds, it's a proxy for the bias risk that we can't measure with because we don't have access to the application distribution. Now this, for binary problem, at least in our field, it's called, in my field, it's called detection cost function, because it's a specialized case for binary problems. Binary problems are also sometimes within the answer to the question true or false, so they can be also seen as detection problem. Do I find my property or not? Do I pass my verification step or not? So I will call it detection cost function. That is nothing else than empirical bias risk as defined for a binary problem where we have zero cost for correct classification and these two costs for false positive and false negative errors, which are also assumed to be positive cost or equal to zero. They can be. So how do we define, we compute the empirical bias risk? We have a data set. If it's a binary problem, we define the cost. For the specialized version of the binary problem, we define the cost of the two different kinds of errors. We define the class prior. These three define the application for which we are computing the error. Cost plus prior gives us a detection cost, error cost plus prior gives us a way to compute the empirical bias risk or detection cost function for the binary problems for this task. Of course, if we have a multi-class problem, we will have a vector of priors and a full matrix of class errors, so of the possible combination of errors. And we can just use the definition we gave before. There is nothing different. We just made some assumption we could show can be used to transform any problem that is binary in an equivalent problem where the bias costs are equivalent in the sense that they would, okay, in the sense that they give us equivalent answers for all the questions we could ask, but we will not see how this is possible. So this is just, for us, it's just the bias error rate for a problem where these two costs are 0 and the cost of false positive and false negatives are greater or equal than 0. Now, this solves two problems, taking into account cost of errors and being independent of the evaluation empirical prior, because now everything is parameterized by the application prior and the cost of errors. We still don't have a normalized value. By looking at the cost, we still don't know whether our model is optimal or not. Now, let me just see. We can, let's do it for the binary problem, then we can generalize it for multiclass. But for binary problem, it's easy to write it down. We can now consider what would be the bias cost of a classifier that always does the best cost that you can do based only on prior probabilities. We will need to prove that this is the case. So for the moment, let's just consider two possible cases. Then we will show that these are the best you can do. But to show that, we need another 1.5 hours of lecture. Let's, for the moment, imagine we have a system which has two options. It can always predict, it doesn't look at the samples, so it doesn't know whether the sample is from, what are the features associated to our sample. It just decides to either predict always class true or always class false. So we consider a system that is dummy. It doesn't make any reasoning on the features. It just decides always true or it just decides always false. We have two options, actually. One system always says true and the other system always says false. Let's consider the cost of each of these two systems. Well, in the first case, every prediction is true. So what does it mean? The probability of a false negative is 0. I never predict negative, so all samples of the true class will be correctly classified. On the other hand, all the samples of the false class will be labeled as true. So for the false class, I will have a probability of a false positive rate of 1. False positive rate is the fraction of samples of class false that are labeled as class true. They are all of them, because my system always says true. So all the samples from class false are labeled as class true. False positive rate 1. False negative rate is how many samples of class true are labeled as class false. Since the classifier always says true, there are 0 samples of class true that are incorrectly classified. So this is 0. Detection cost, let's plug these values inside. If I plug these values inside, what remains is just this term. Just this term with PFP equal 1, of course. So it's this cost. Every time I have a false samples, I will make a mistake. So the average number of mistakes is this, and each time I have a mistake, it will cost me a false positive mistake. So this is the cost that I will pay on average if I use this system. Then I can repeat the same with the other possibility. Always predict false. In this case, the two rates change. My cost will be this. If I always predict false, every time I have a true sample, I will make an error of the kind false negative. So this is the cost that I will pay if I use the second system. Now, notice that this depends only on the application information. So when I define my application, I can measure these two costs and decide which is the best system, the best option. So I can always build a system that has the minimum of these two costs, because I can always build both systems, measure their performance, and then choose to use the one which has lowest cost. So the cost of a dummy system that always predicts a single label will be the minimum of these two, assuming that I will select the system that has lowest cost among these two. So this is the cost of a dummy system, and I can use that to normalize my DCF. This gives me a cost that is a relative cost with respect to a system that doesn't look at the sample, but always predicts a single class. And which one it predicts? It predicts the one that will give me on average the lowest cost. This is called normalized DCF, and it has the property that we lose the cost interpretation in the sense that if it costs were euros, now these are not euros anymore. This is a relative cost with respect to a dummy system. But we have the property that if this is greater than 1, it means that our system is worse than a dummy system. So our system is making damage. We should not use the system at all. If it's lower than 1, it means that our system is better than if we didn't do anything. If we don't do anything, it means that we have to choose one of these two actions. We will prove that actually these are the only options that are available, and the lowest cost of these two is actually the action that we should take. We don't have enough for the moment to prove it, but we will show that one of these is the optimal choice we can make. We cannot do better than this. If we don't look at the samples, then the best we can do is to choose to choose the best of these systems. So we know whether our classifier is extracting information from the data that allow us to do better than if we didn't use, than what we could achieve as optimal if we didn't use any recognizer. So in this sense, the normalization tells us whether the classifier is useful at all. Finally, when we work with normalized DCF, we can observe that the normalized DCF is invariant to a rescaling of the DCF. That is, if we define it with, we define the normalized DCF as what? As the ratio between the DCF computed for our recognizer divided the DCF computed for a dummy system, the best dummy system. If we rescale both detection cost function by a factor alpha, so rather than using the original DCF, we use alpha times the original DCF in both cases, we will still get the same normalized cost. So we can take our DCF and use this strange scaling factor, which may look strange, but we define a unnormalized DCF that is obtained by taking the original DCF for cost of false negative, false prior, and pi, and divide it by this cost. So we use this new DCF, let's call it DCF prime, and then we define our normalized DCF in terms of the DCF prime. So here we use DCF prime, so all of these will be scaled by the same factor, okay? The normalized DCF remains the same because the scaling factor will be the same for both numerator and denominator. How would the new unnormalized DCF become? Well, you can take the original DCF, write it down, and you will see that you could express it in this way, as probability of false negatives times a factor pi tilde plus probability of false positive times a factor minus 1 minus pi tilde. But this is what? This is the original DCF for an application which has pi tilde as prior and cost of errors equal to 1. That is the same normalized DCF if we consider an application that has prior pi t, cost of false positive and false of false negative given, and we consider an application that has a prior pi tilde given by this relationship, then these two applications will have a different unnormalized DCF, but the normalized DCF will be the same. The normalized DCF for these two applications will be exactly the same, regardless of, well, as long as this pi tilde is defined in this way. Which means that if we measure everything in terms of normalized DCF, these two applications are equivalent. Now here there is again that doesn't make sense because we never defined this to be equivalent. These are left over from when I moved these slides up, because we see another place where these two applications will be considered equivalent, but it's actually afterwards in the slide. So this again actually refers to something that previous year was before, now it's after. Sorry, I need to remove it. But in terms of normalized DCF, these two applications are the same, which means that we can always, when we use normalized DCF to measure our performance, parameterize everything with a single value. This single value for binary problems is called effective prior. That is, if the class prior was the effective prior and we consider the cost to be uniform, then our effect, our performance would be the same as if we were considering the original prior with non-uniform costs. So actually there is only one really free parameter, the effective prior. We can always reparameterize a binary application in terms of an effective prior that condenses the application prior and the cost of the error rates and behaves as if this was the actual prior of the application and the cost of the errors was the same. This will be useful, well, when we see this appearing elsewhere. Now, for the moment, this is not particularly interesting. It will become interesting when we say this property appears when we also make our decisions, and there it will be useful to define a simple way to consider different applications in one shot. So for the moment, we just keep it there as information. We will recover this later. Now, if you want, you can do the opposite also. You can take one application which has a non-uniform prior, and you can transform it into an application which has different costs and prior 1/2. So if you want, you can always parameterize an application as an application which has the same prior for both classes, but the cost of errors will change to reflect the fact that the priors are different. But we will not use this, so we will not need this. Now, as we saw at the beginning, the error rate is 1 DCF. It's an unnormalized DCF with a prior equal to the empirical prior. So this scaling factor here refers to the fact that corresponds up to the scaling factor to the normalized DCF of this application, and it actually is exactly the unnormalized DCF of this application. So the error rate that we measured at the beginning corresponds to an application where the empirical prior is the application prior and the cost of error rates is the same, which is not necessarily our target application. Then maybe you have seen other error rates defined as, for example, the average of the error rates of the two classes. Again, this is an example of DCF, an application with costs equal to 1 and prior class probability equal to 1/2. So many different measures can be cast in as a specific case. Let me see. Okay. Okay, let me see. Just I thought I had the example with cost for the has problem, but I don't see it here. Just give me a second. It is also. Così. Okay, I don't see it here, but just to go back, since empirical class prior, since we can parameterize applications, we can parameterize the cost of error rates in terms of changing the application prior. You can imagine that we have seen before in the example that we gave, the change in the application prior changes the relative performance of systems. Adding costs for a binary problem, we said, is equivalent to changing once more the application prior, because the cost can be represented as a change of the application prior, that is by using the effective prior. Then you can imagine, I don't find the example here, but you can imagine that if I change the cost for the different kind of errors, then the relative performance of the systems, as it was changing before when I just changed the prior, will also change when I add inside the classification error. For example, here you can just take the false positive and false negative rate, keep, for example, the prior 0.01, but now add cost for the two kind of errors. So for add different costs, adding different costs, you can compute what happens to the empirical bias risk for the two classes and see how the cost would change the relative performance of the two systems up to some point where R2 would become, again, more competitive with respect to R1, when the cost essentially of this kind of errors, becomes much smaller than the cost of the other kind. So here, if I predict negative and the sample is positive, why this model was penalized? Because I have a very few amount of samples on the positive class, but if the cost of this error becomes much, much, much larger, even if I have few samples, every time I make a mistake of this kind, it will again cost a lot. So at some point, I will again prefer this classifier that spends less. Maybe it's in the slides after this, but I don't remember where I put the example. I thought it was there, but maybe it's later. Let me see if it's later. No. Okay. Now, for today, let's finish this part. Then tomorrow we'll see how to make optimal decision. Now, for binary, we've seen how to define a decision function, a detection cost function. For multi-class, we can resort to the empirical bias risk. And again, we can normalize it if we want by consider dummy systems. In this case, we have k options. Each dummy system predicts a single class k, and then we can measure the cost of each of these k systems, take the one that has lowest cost, and use it as normalization factor for our empirical bias risk. So it's the same thing, we just need to consider all possible k options rather than just the two options we did for binary. Now, tomorrow we'll see how to make bias decision, but let's focus again still some more on binary, because for binary problems, we can also define other interesting objects that we can use to analyze the performance of a system. For this kind of problems, we have seen that for binary classifiers, typically our classifiers will output a score with the idea that the highest the score, the more we favor class true, the lowest the score, the less we favor class true. Typically, our decisions will be compute the score for a test sample and then compare it with a threshold. That's how we were making decisions up to now for binary problems. Compute a score and compare it with a threshold. For generative problems, I recall that we were using a threshold minus the prior log odds. Why? Because we have seen that this corresponds to making a classification that gives me the class with highest posterior probability. But we will now refine this, but in any case, we were always doing this kind of problems. Compute a score and then compare it with a threshold. Typically, higher scores we favor class true, lower score we favor class false. This we have not seen yet, but we will see that also the classifier we have yet to see follow this idea. Now, if this is true, we can visualize, for a binary problem, we can visualize how the threshold affects the quantities that we have defined. Remember that the bias risk, the empirical, the detection cost function depends on the cost. This defines the application, but then this is defined by the application. What else appears in the cost function? The probability of false negative and false positive. So the false positive and false negative rates. These are the 5 quantities that are required to compute the DCF. This depends on the application. This depends on our classifier. These are characteristics of the classifier for that specific task. So we can try to visualize for a binary problem. For a binary problem, we said the decision corresponds to comparing a score with a threshold. We then visualize how these affect, how the selection of the threshold affects these quantities. For example, imagine that I have run my classifier over a large number of samples. Then I take the true samples and the false samples, and I plot the histogram of the scores for the two classes. So I have taken class true, lots of samples of class true, and computed the score. Then for class false, lots of samples for class false, and computed the corresponding score. Then I take the two set of scores and I plot a histogram. If I have enough samples, this will look like a distribution density. So let's plot a distribution density for the score samples. But this should actually be a histogram because we always work with actual data. Now we said the red line is the histogram that corresponds to the samples of class true. The blue line, the histogram that corresponds to samples of class false. The dashed line is the threshold at which I cut my samples. So if I cut at t, what happens? This fraction of samples here will be samples from class true that are correctly classified, true positive. So remember that the errors of this curve sum up to 1, so the area that is between the dashed line and below the red curve is the false positive, the true positive rate. So if the area of the histograms are normalized, this area is actually the rate. The green part is what? True class that are predicted as false. This is false negative rate. Then we have here true negative rate, the blue one below the blue curve before the threshold, and then I don't have a light blue, so I will do it in black. this part here is negative class predicted as true, so it is false positive rate because it's normalized, because the error of the histogram is 1. So we can see that as we move the threshold, the two error rates change. We can move the threshold and change the weight of the two contributions to the cost of errors. Now, since in my formula these two contributions are weighted by different weights, because the empirical bias risk weights each of the error rate by the corresponding cost and the corresponding class probability, changing the threshold, I can change these two costs. These two costs do not have the same weight. Changing the threshold will not change them in a linear way. So changing the threshold will typically change the final cost of my system. So the way I cut my system at, by the place I put my threshold, will change the false positive and false negative rate, and therefore will change the empirical bias risk. So I can, for binary problem, control the empirical bias risk by controlling where I put the threshold. The threshold is important because different threshold will change the empirical bias risk. Remember, for example, when we were trying LDA with different thresholds, you probably didn't try very extreme values of the threshold, but if you tried very extreme values, you would see that your error rate would jump up to 50%. Well, no, not 50 because it was not perfectly balanced. It's whatever corresponds to the empirical prior of your data set, and whether you put the threshold on the right or on the left. But in any case, something close to 50% because the split was essentially almost balanced. While for thresholds in the range that we defined when we were in the laboratory, the error rates were much, much smaller. This is exactly what's happening. If you move the threshold too much on one side, you will have that for one class, you will have all points that are incorrectly classified, but do very good on the other class. Depending on the cost of the errors and prior probabilities, this may reduce or increase your bias error cost. Before we see tomorrow how to find the optimal threshold, we can use some graphical tools to actually see the impact of the threshold on our systems. Tomorrow we see how to choose the optimal threshold, but for the moment let's try to see some way to see how the model behaves in a way that is independent of the threshold, or to be more precise, that takes into account possible values of the threshold. One possible way, we can start visualizing our false positive and false negative rate as a function of the threshold. This tells us, for the two classes, as we move the threshold, what are the error rates that we have for the two classes. And from this, then we will see that we can build something better that gives us the empirical bias error for each sample. But we'll see that next week, tomorrow. For today, we stop with this. The other thing that we can do is, as we change the threshold, we see that we have a different value for the false positive and false negative rate. We can imagine to draw a parametric curve where the curve is parameterized by t, and each point of the curve corresponds to a different threshold. And for each threshold, we put the false positive and false negative rate. Typically, in ROC curve, you don't put false negative, you put true positive, but that's the same information. We said it's just 1 minus, so it's just flipping the axis. This gives us, for all possible applications, what are the corresponding error rate. Notice that it doesn't tell us on which is a specific application. So we don't know by looking at this curve what is the application that we want to solve. And it doesn't even allow us to compare two systems directly, because it allows us to visualize that there are regions in space where one system is better, but we need to know where our application is to know if for a specific application the system is better. Alongside ROC curve, we have what are called dead curves that are the same information, just flipped axis, on a scale that you see is not linear. the scale is not linear and is chosen so that this curve for Gaussian distributed samples becomes a straight line. So it's just a way to see, rather than seeing the curve linear, non-linear with a linear scale, you have a non-linear scale of the axis where specific classifiers will correspond to straight lines. Again, each point of this curve corresponds to one threshold, and these curves are useful because they allow me to compare different classifiers at different positions. So, for example, if we have recognizer 1, recognizer 2, and recognizer 3, we can conclude that for problems where we are interested in having low amount of false negative rate, then, well, for all system R3 is better, for all application R3 is better than R2. Then if we want lower false negative rates, then we probably should switch to R3. If we want lower false positive rates and we don't care about the false negative rates so much, then R1 is probably better. But notice that then we will need to know our application to which point on each of these curves corresponds to know if for a specific application our classifier would be better. Why I say application? Because we didn't prove it, but we'll see that tomorrow. Each application will give us way to define a threshold, and the threshold will be optimal. The optimal threshold will be a function, again, of the application parameters. But this we will see it tomorrow. So for today, I think it's enough.